All right, we're recording now. Let me take my keyboard off. There we go. Yep. All right. Good morning, everybody, or good afternoon, or good evening, whenever you watch this. This is the video that I promised right before we went on spring break, a discussion on how to perform your pre-lab calculations for the next experiment that's going to be for the buffers lab. I'm going to talk a little bit about an assigned pH in addition to where you can find the files of interest so that you can follow along, because this information, at least the file that I'm using here for like these questions, is not included in a note packet that I printed out for y'all. Thankfully though, I did post on the Canvas site where you could find the file. So here on the screen, you'll notice that I have a kind of a mock diagram of our laboratory where we have, let me grab my laser pointer here, we have the entrance to the lab. This is where everybody enters into the laboratory. That's going to be NAS 319. We have the exit on the other side. This is where the whiteboard is. I didn't draw both fume hoods because I know we technically have another. Actually, do we have two fume hoods in that room? No, we only have one fume hood. I'm thinking about the organic labs. Apologies. So yeah, we have the fume hood on the opposite end, and then of course we'd have windows and the balances back here. The reason I've drawn this up is because depending on where you're located inside of the laboratory, you're going to be assigned a pH to make a buffer solution. Excuse me, I'm drinking my daily dose of caffeine here in the morning. I guess I should say, I hope that y'all's break is going well. I'm very sorry that we have to do this. Especially the Monday lab, because the Monday lab is going to have this completed by the time they walk into the laboratory on Monday. So I'm going to assign 3 different pHs for every single bench. So you have to remember where inside the laboratory you're seated. So this is the central bench, this is the bench closest to the entrance, and this is the bench closest to the fume hood. I'm just going to call it 1, 2, and 3. And I have 3 different pH values that I'm going to assign to each bench. So if you are, and what I mean by this is the goal of the buffer experiment is to make a buffer that works at the pH that I assign to you. Meaning, if you add any amount of acid or base to it, we should suspect the pH to not change by a huge amount, or so it's only going to change by a few values, right? Not even an entire value, like decimal, tenths, if not hundredths of a value as we add acid and base to it. Okay, so at the beginning of lab, you're going to walk in, and once everybody is seated, I'm going to walk through everybody's, or what other calculations have to be completed for this lab, just like I usually do. And then before you can start any work, I have to check everybody's calculations. And remember that if you do not complete your calculations for the lab before you walk into the laboratory next week, you will get a 0 for the lab. So please be sure that you complete the pre-lab calculations. Otherwise, you will receive a 0 for the lab. I repeat, you will receive a 0 for the lab if you do not complete these pre-lab calculations. And you're going to see the exact same information, or you've already seen it when I make the announcement, because I'm going to make an announcement on Canvas about this video, along with the blank notes that you can take. So what I'm going to do here is I'm going to assign some pH values. I have 3, 1, 2, let me see. Yeah, let's do 3 here. So the first pH value, if you're closest to the entrance, that is the pH that I'm going to write down in red here, your assigned pH is 4.35. If you are in bench 2, that is the one that's been assigned the blue ink right here, then your assigned pH is 5.15. And then if you're on bench 3, that's the one closest to the fume hood, then your assigned pH is 9.60. Now, for some odd reason, you do not know where you sit based on this little diagram, which I don't expect. But if somehow it's already it'll be week 9 when we come back. If we come back on week 9 and you still don't know where in the room you're seated, for whatever reason, maybe you just didn't think about the orientation of the room here, I'm going to write the following little star. If you do not know where you sit, you are assigned pH equals 5.00. In fact, I believe the lab manual says the same thing, that if you were not assigned a pH value, just use 5. So for some odd reason, after 9 weeks of being in the laboratory, you still don't know where you sit in the lab, then your assigned pH is 5. And then my next comment is, how do you not know where you sit in the lab? We've been in this room for like 9 weeks. So that's just Dad Ochoa being very like, come on now, you should know where you're seated in lab. All right. So what I'm going to do for the next probably, I don't know, it's probably going to take me like 30 minutes to go through all the calculations. I'm going to talk about where you can find the blank file for this discussion point here. And I'm going to run through the calculation for a pH that's assigned a 4.30. I know that some of you might be thinking, ooh, I have 4.35. So if I just follow 4.30, I don't have to do my calcs if I'm on bench 1. No, there's enough of a differentiation between 4.35 and 4.30 that you're still going to have to perform these calcs on your own. So I'm going to complete the calculations for 4.30 as if this was the assigned pH that an instructor gave me or the professor gave me. It will be your job to walk through the calculation for your assigned pH. Now, I did a little bit of the work for you already. At the bottom of this page, you'll notice I have pairs of acids and their conjugate bases. Acetic acid, acetate ion, phosphoric acid, phosphate ion, or hydrogen phosphate, dihydrogen phosphate, and so on for the rest of them, carbonic acid. I do believe that oxalic acid should also be included in here. I do apologize that I didn't. So that's something that you will have to find on your own time. Although I don't think, looking at the assigned pH values, I don't think you have to use oxalic acid. So I might not even include it. So you can almost just disregard that last sentence that I said. So before we get into this calculation and along with the questions, I've also made a mock like table 2. This is something that you have to complete in your lab notebook before you walk inside. It looks a little bit different than the way it looks in your lab manual. That's just because instead of it being stretched out over like two columns of data, it wouldn't fit on this page. So I just kind of stretched it out as just one column where you fill in that information. I'm going to fill the information in here so you kind of know what you're supposed to write in for your calcs. So I'm going to put this on the announcement in addition to, of course, in here. Remember, this is double star. Failure to complete Prelab results in 0 for lab. So I've warned you verbally. I've warned you me writing it down in this video. I've warned you. There's gonna be a warning in the announcement. So it's Thursday. It's Pi Day. Oh my God! It's 3/14. Happy Pi Day, everybody. There is more than enough time for everybody to complete the pre-lab calculations before you walk into lab on Monday or Wednesday. So With all due respect, you have no excuse. All right, let me adjust my microphone here for a second. Okay, so going to the Canvas site really quick. So I've set this to student mode. Some of you may have noticed that I posted the practice exams for the next midterm. So if you did not see that announcement, because I'm pretty sure I made an announcement, they are available for you. I will, of course, provide printouts of the practice exams once we actually return to class on Tuesday. But if you want to get a head start, that information is available to you. At the very top of the home page, I've added a new module, Experiment 8, Buffers Prelab Calculations. Now, by the time you see the home page, this module is also going to include a link to the annotated notes for this discussion, and it's also going to include a link to the YouTube video where I'm talking about the recording itself. So it's going to be a little bit different than what you see on the screen, but that's because I haven't actually posted it yet. All right, so let's go back to our discussion here. Yeah, going back, this is just the blank notes that I would normally like print out for you. So it would look exactly like this, except of course it'd be on white paper and black text. So here's the pre-lab calculations. You are assigned the pH of 4.30 for this laboratory, and you need to determine the following. The first question that we have to answer is, which of the following acid, along with its conjugate, are you going to choose to make the assigned pH? So in the laboratory, we're going to have available to us acetic acid and acetate, ammonia and ammonium, I believe just phosphoric acid, carbonic acid, and again, I think there's going to be oxalic acid, but you won't have to deal with oxalic acid. All right, so that's the first question. We have to choose the right acid conjugate base pair to make the buffer of the assigned pH. Because if we choose the incorrect acid base pair, then when we make our supposed buffer solution, the pH range of that working buffer is way outside of the assigned pH that we were given. So you have to, and this is, it sounds more complicated than it really is. I'm gonna explain to you how you're supposed to select the correct buffer. All right. The second question is, we need to determine the ratio of how much conjugate base or acid or base to acid we need using the Henderson-Hasselbalch equation for the assigned pH. So instead of having to solve for pH using the Henderson-Hasselbalch equation, we're working backwards. We're trying to figure out what's the ratio of the log of B over A. Of course, we're going to get rid of the log. We just want the ratio of B over A. And then, once we know what that ratio is, we can determine how much of a strong acid or base is required, or I need to add to the buffer to force it to be the pH that has been assigned to me. Because when I make let's say as an example, I've made an acetic acid solution with no sodium acetate. The goal here is you're going to make a solution that's just acetic acid and you're not going to add sodium acetate. And because it's only acetic acid, the pH is going to be lower than the assigned value that we expect it to be. This is just like a standard dissociation of a weak acid, right? And so the goal here is to figure out how much, as an example, I'm using acetic acid, and in fact, that's what I'm going to use for this discussion. How much strong base do I need to add to this acetic acid buffer to increase the pH to what has been assigned to me? If you were assigned, let's say, ammonia, and the pH is too high, meaning let's say the pH was 11, and my assigned pH is 9.6, and I have to add HCl to the solution to drop the pH down to my assigned value, okay? Once you've answered those three questions, you will have all the information required to fill this table out. So let's get started here. I don't have a mouse, I just realized. Where's my keyboard? I am going to need my keyboard, as it turns out. I would have a mouse, but I'm using my work mouse for my desktop because my actual wired mouse, this is just Dr. O ranting right now, my wired mouse, the little window on the bottom where the laser comes out, I cracked it. And so it barely works. And it's very frustrating to do any work with that mouse. In addition to trying to, like, Dr. O has been trying to play some video games over the break. And I've been trying to play, for those who may not know, Dr. O is a very big avid fan of like old school first person shooters or ones that are like very quick. So Dr. O has been playing Doom Eternal, and let me tell you, it's really hard to play Doom Eternal when your mouse is not working. But I am getting it to work with my work mouse. I had to order a brand new mouse because of that, because I was probably too violent with my mouse placement. Okay, back to the discussion. Tangent over. You're assigned the pH of 4.30. Determine first which of the following acid or base do you use from the table below to make the assigned pH. So to answer part A, when you're trying to create a buffer, select an acid conjugate base or a base conjugate acid pair that has a pKa closest to the pH of interest. So I need to find a pKa that is really close to 4.30 because that's the pH that's been assigned to me. Now, I took the liberty of actually calculating the pKa of these acids along with their conjugate bases. And so I most definitely do not want to choose, let's say, hydrogen carbonate and carbonate ion because that pKa is really far away, right? I don't want to choose one of the conjugate pairs of phosphoric acid and phosphate. I just realized that the phosphoric acid hydrogen phosphate is actually paired up incorrectly. Let me fix this really quick. So this is supposed to go down here. That's supposed to go right there. Oh, okay, I see. My apologies. I must have made this when I didn't have enough coffee here. So the phosphoric acid, the first pKa of phosphoric acid should actually be 2.12. So let's do this. 2.12, and then this should be 7.21, and this should be 12.38. I'll have to fix that later. That's my bad. Let's just blot these out. All right. Those are incorrect. Okay. So I'm trying to find a pKa that is really close to 4.30. So really you're looking for the smallest difference, right? 2.12 is still pretty far. 7.21 obviously is really far. 9.246 for the pKa of ammonia and ammonium is really far. But acetic acid and acetate has a pKa of 4.74. That's really close. So I think what I'm going to do is I'm going to choose this acid conjugate base pair because the pKa is so close to 4.30. Wink wink, if your assigned pH was 4.35, that's going to be for bench 1. I've kind of already told you which acid you want to use, right? All right. And in fact, you could say the same for pH 5.15. And then for pH 9.60, you'll have to do a little bit more thinking. Hint, it's probably ammonia. I pretty much gave everybody the answer to their assigned pH value. Okay, so I'm going to choose for part A, for the assigned pH is equal to 4.30. Choose acetic acid, HC2H3O2, with its conjugate, C2H3O2 minus. So that answers part 1. We've already done part 1 of this, so I'm going to put a little check mark here. We're done with that. Now we actually get into the math. Part B is determine the ratio of the conjugate base or conjugate acid to base or acid for the assigned pH. So for part B, I need to use the Henderson-Hasselbalch equation. And I'm trying to figure out what is the ratio of B over A. And I'm going to use that ratio to determine how many millimoles of the base and the acid I need to make that assigned pH. So really, the difficult calculation is part B and C. I will say that C is probably more difficult than B, because B is just the Henderson-Hasselbalch equation, right? So moving on to part B, use HH equation. So the Henderson-Hasselbalch equation is pH is equal to pKa plus the log of the activity of B over A, or the molarity of B over A, or the moles of B over A, right? Remember that B over A doesn't actually have units because everything is with respect to activity, okay? Which, not for this lab, but for the next lab, experiment 9, when we actually do our titrations, we're going to do something kind of interesting with our Henderson-Hasselbalch equation. So I have virtually all the information to figure out what the ratio of B over A is. That's just a number, right? So for the sake of, I want to reorganize this equation, okay? So I'm trying to solve for B over A, and just B over A, not the log of B over A. So I'm going to move first, I'm going to subtract pKa to the other side, so that we have pH minus pKa is equal to the log of B over A, where B is the acetate ion and A is the acetic acid. Now I want to get rid of the log. In order to get rid of my log, remember that if you look at your calculator, if you forget, the opposite of natural log is an exponential. The opposite of a log is 10 raised to a value. So to get rid of the log, I'm going to do 10 raised to the pH minus pKa, and that will be equal to the ratio of B over A. And it's just going to be a number. I'll explain what we're supposed to do with that number in a little bit. So now I'm going to plug some numbers in. 10. And remember, when you do this calculation on your own, you're going to use your assigned pH. So once you figured out what your pH is, or what your assigned pH is, and then you figured out which pKa value, you can walk through this in the video just using your values. You can run through it twice just to make sure, you know, the theory makes sense with my value that I'm doing right now, and then you can use your values later down the line. So the assigned pH for this example is 4.30, so it's 10 raised to the 4.30. Let me zoom in on this a little bit. Let's rewrite this. 4.30 minus the pKa of acetic acid, which is 4.74, is equal to B over A. And when I plug that into my calculator, the ratio, and let's actually write this down. So it's the the concentration of the acetate ion, C2H3. Remember that it's not actually concentration, it's just activity, over the acid form, HC2H3O2. And if I plug that into my calculator, which I'm going to do so right now, I have my notes in my screen on my desktop right now, but I want to make sure that I'm doing this right. 10 raised to 4.3 minus 4.74. I get 0.363. So that's the ratio of the acetate ion to the acetic acid molecule. All right. This answers part B. All right. To answer part C, so let's go back here and put another check mark because we did part B. Part C is determine how much of a strong acid or base is needed. You need to add this to the buffer, or you need to add it to just the acid or the base to force it to become the pH that has been assigned to me. Determine how much of a strong acid or base is needed to make the assigned pH buffer. All right. Because what we're doing in lab is we're only giving you one of these. Of course, if you're working in a different laboratory, you could figure out the concentration of both of these. This would be a solution. This would probably be a solid salt of some kind. You can figure out how much of this you need in concentration and then that would give you the pH directly. But here we're only giving you one, and you have to force the reaction to make the other by adding either HCl or sodium hydroxide, just like we did our titration curve in class last week. All right. I need to insert another page so that we can create an ICF table. So we're going to make an ICF table, and we're going to work backwards. All right. Now let me make sure that I'm still recording. Let's go back to OBS here. I am still recording. That's good. I've been recording for 30 minutes. I guess this video is going to be a little bit longer than I thought it would be. All right. Let's change colors one more time. Let's do green. C. Okay. So to figure out what amount of strong acid or base we need for the assigned pH, we need to work backwards in our ICF table because we don't know how much we're adding. We're trying to figure out how much we need to add. Okay. Now, for the laboratory, the goal is to make a 100 milliliter. You're going to make 100 milliliters of a buffer solution. So this is actually the applied how much you're supposed to make in the laboratory. And then you're going to take certain volumes of this 100 milliliter buffer that you make, and you're going to perform experiments on it. Okay. All right. So the assigned volume for all buffers is 100 milliliters from a stock solution. The goal to answer this question is to determine, so I erase this really quick, determine first how many moles of the acid / base are in the flask to begin with. Oops. Let me actually write out with here. So when you walk into the laboratory, you've identified which acid conjugate base pair you're going to use to make your buffer solution. Now you're going to go into the laboratory and find either the acid or the base form of one half of the buffer. You know, let's say, so as an example here, my buffer has a pair of acetic acid and acetate ion. So I'm going to go into the laboratory to try and find either the acetic acid to place in my flask or the acetate ion to place in my flask. Now, in the laboratory for this example, I'm going to start the calculation with acetate ion. So my assigned volume is 100 milliliters of a 0.1 molar solution of sodium acetate. And it's important to note that when you make your buffer solution, you're probably going to make it from a straight solid first. So here is just the concentration of the acetate ion, 100 milliliters of 0.1 moles per liter. And I'm trying to figure out how many millimoles are inside of that flask, right? So I'm going to convert from molarity, so concentration of the acetate ion is 0.100 molar in 100 milliliter flask. I'm trying to figure out how many moles are there in here. So 0.100 moles of acetate, which I'm going to abbreviate as AC minus because I don't want to write down the entire chemical formula. 0.100 moles of acetate per liter, and I have 100 milliliters. And I'm going to leave this in milliliters so that when I complete this calculation, I'm left with millimoles, just like we did our example in class, simply because it makes the math look prettier. I don't have to deal with scientific notation. I don't have to deal with reading out 0.0001 moles of something or 0.0235. It's a lot easier for us to mentally digest values that are like near whole numbers, right? So plugging this into my calculator, 0.1 times 100 gives me 10. So there are 10 millimoles of the acetate ion inside of the flask, which, by the way, the flask is a volumetric flask. Okay. Now I have to figure out how much let's say strong acid or strong base do I have to add to make the ratio of the acetate ion to the acetic acid molecule equal, what was the value? 0.363? 0.363. All right. So now comes the part where I'm going to use my my ICF table. So let's get another page going here. Insert page. All right. So I'm going to create an ICF table where the reaction is the acetate ion C2 H3 O2 minus aqueous reacts with HCl. Remember when we put HCl, and the reason I'm using HCl is because when I make sodium acetate, the pH is going to be way higher than 4.30. It's going to be like, I don't know, 7. And I have to add some amount of HCl into the solution to force the pH to come back down. to 4.30. Okay. Now, I'm not going to write down HCl here because I know that the second I put HCl inside of water, it's going to become a proton and a chloride ion. And the chloride ion is just, it's a spectator ion. I don't care what the spectator ion is doing. This is also true for the sodium ion for, let's say if I made the solution out of sodium acetate, the sodium is just a spectator ion, which is why I don't include it inside of my calculation here. This is true for any acid-base reaction that we do. Almost, I would say 98% of the time, the counter ion to a conjugate base or the counter ion that would be, let's say, an anion can be excluded from virtually any calculation because we know that it's a spectator ion. So this is going to react with H+. And remember, this is an ICF table, not... this is an ICF table and not an equilibrium. So this is going to go, because this is an acid-base reaction, to make HC2, H3O2. Let's include our state symbols here. We want to be consistent. ICF. The initial amount of the acetate ion is 10 millimoles. I calculated that up here. So that's going to be 10.0. All right. The initial amount of acetic acid, we're going to assume is equal to 0. And the initial amount of protons that I have to add to the system is the question I'm trying to answer. That's X. I'm trying to figure out how much HCl do I have to add to the system to force it to create the ratio of 0.363, right? And we know that the amount of acid that I add to the system is going to be the limiting reagent. So all of the HCl, all the proton that's been introduced to the system from the dissociation of hydrochloric acid is going to be completely consumed. So the change is going to be towards the production of acetic acid, which means it's going to be minus X, plus X. So 10.0 minus X. We're going to say X here. And in fact, yeah, that should be fine. I know it looks kind of weird that it's X minus X and this is also equal to X. Let's do this instead. Let's say we're trying to figure out what this number is, okay? And then X. All right. So now, here's the deal. If I can figure out what amount of acetic acid I made, that's also going to tell me how much of, let me put a minus here, sorry. That's going to tell me how much proton I have to add to create this amount of X, right? So, what I'm going to do is I'm going to use the ratio of B over A, which happens to be equal to the ratio of acetate ion over acetic acid is equal to 0.363. And that ratio is equal to 10 minus X over X. If I can figure out what X is equal to, then I can determine what amount of proton I have to add to the system for it to be completely consumed. Right? I guess this should be 0, right? I know that's going to be 0. All right. So let us solve for the expression of 0.363 is equal to 10 minus x, 10.0, sorry, over x. I'm going to, let's say, move this x to the other side, so I get 0.363 x is equal to 10.0 minus x. I'm going to add x to the other side, which gives me 1.363 x is equal to 10. And then I'm going to divide both sides by 1.363. So let's see. Let's make sure that that makes sense here. Yeah. 10 divided by 1.363 is equal to 7.34. Okay. Now, what I can do, if I know that this x is equal to 7.34, then I know that the initial amount here, let's call this a minus x is equal to 0. A minus 7.33 millimoles is equal to 0, which means the amount of acid that I have to add is 7.33 millimoles. Okay. Fantastic. All right. So this tells me how many moles of acid I have to add to the system. I'm going to do a conversion in a second to figure out how many milliliters I have to add to the system, right? Now, before I get to that, I want to figure out, hey, what amount of sodium acetate do I have to add to the flask so that the concentration of the sodium acetate to begin with is 0.1 moles per liter, right? We're going to do that calculation first, and then we're going to go back to figure out what is the volume of HCl that has to be added to the flask to force the pH to go down to 4.30. So on the next page, man, acid-base chemistry just has, it's so much work, right? I was expecting this video to be only like 30 minutes, but as it turns out, it's way longer than that. How much sodium acetate, C2, NaC2, H3O2, and it's in the form, the sodium acetate you're going to, this is of course if you're using acetic acid and the acetate ion to make your buffer solution. It's going to be different if you have to use a different acid conjugate base pair. But the acetic acid or the sodium acetate that you use in lab does not come in the form of just sodium acetate. It's sodium acetate trihydrate. So how much sodium acetate trihydrate do I need to make 100 milliliters of a 0.100 mole per liter or molarity concentration? So this step is just stoichiometry. All right. So I have, let's see, 0.100 moles of the acetate ion, which I'm going to abbreviate AC minus per 1 liter, times how many milliliters am I making? 100 milliliters. So this is going to be 0.10000 liters because you're making it inside of a volumetric flask. And a volumetric flask is 100.00, goes out to the hundredths place, so we have to include all that in our significant figures. So now, in blue, our liters cancel out. And I have to convert this from moles of acetate ion to moles of the solid sodium acetate trihydrate. Luckily, it's a 1-to-1 mole ratio. I am going to show that calculation here. So for every 1 mole of acetate, we have 1 mole of NaC2H3O2 trihydrate, not one hydrate. This should be 3 water molecules. And we must consider those 3 water molecules when we perform our stoichiometry, because we're going to convert it from moles of sodium acetate trihydrate to to grams of sodium acetate trihydrate. So let's continue this down here. So here we see moles of acetate cancel out with moles of acetate. All right. And let me make sure. I do believe it is. Yes, it's sodium acetate trihydrate. Okay. It is inside your manual. I just wanted to make sure. All right. So for every 1 mole of NaC2H3O2, 3 waters, you have 136 grams. And the molar mass is actually given to you in the manual. I think I have the manual up right here. So let's go. I do. Perfect. So if I go to page 8 dash, where is it? It should be in here somewhere. I may have gone a little bit too far. Oh, here it is. Perfect. So the molar mass of sodium acetate trihydrate is 136 grams per mole. So there's 136.00 grams of NaC2H3O2 3H2O. Let me erase that too. Look kind of funny. And that oxygen. O2. And here in blue, we see moles of the salt, cancel with moles of the salt, and what I'm left with is grams. So now I'm going to go to my calculator and do 0.1 times 0.1 times 136.00, 1.36 grams. I need 1.36 grams of this salt in my volumetric flask. That's the first half. The second half now is how many milliliters of hydrochloric acid do I need to add to force the pH to be 4.30? Because again, if I dissolve this sodium acetate trihydrate in water, the pH is not going to be 4.30. It's going to be much higher than that. You could do your own calculation later for what is the pH for the dissociation of sodium acetate in water, because you know what the concentration is. You can do, it's 0.1, and then you'd have to figure out the kb and stuff like that, but we're not going to do that here, okay? So the next question to answer is, how much HCl needs to be added to the flask? I know how many millimoles of HCl have to be added. I solved for that in that ICF table. That was the calculation at the bottom of this page. The ratio of the base over the acid is equal to 10 minus x over x. We solve for x, and we know that A, which is the initial constant or the initial number of moles of the protons added to the system minus the X value, which are going to be the same, will be equal to the amount I have to add. Because I know that the amount of acid that I'm adding to the system is a limiting reagent. It's going to run out, right? I have to add 7.33 millimoles in the form of a volume. The stock solution of HCl in the laboratory is 1 molar. So if I know I have to add 7.34 millimoles of, I'm just going to call this HCl because I know that the proton amount that I add is also equal to the initial amount of HCl because it's a strong electrolyte, right? Times 1 liter over 1.00 moles of HCl. This is just the concentration of HCl turned upside down, right? So that my dimensional analysis works out here. And I'm leaving the units of HCl to begin with in millimoles because when I perform my dimensional analysis, moles is going to cancel out with moles, and what I'm left with is milliliters. So I don't have to worry about calculating, converting from liters to milliliters. It's already in milliliters. I'd be done. So this is I'm not even going to plug this into my calculator because it's 7.34 times 1 over 1, which is the same as 7.34 times 1, which is equal to 7.34. So the amount of hydrochloric acid that I have to add to the system is 7.34 milliliters. So here's what I'm going to do. I need to move my big old keyboard here. Let's make sure I'm still recording. I am still recording. Oh man, this is an hour-long video. My goodness. All right. I'm going to insert a page for you to give you a graphical representation of what you're supposed to do in lab to create this solution. All right. I have a 100 milliliter flask, a 100 milliliter volumetric flask. Crude drawing, but it gets the job done. And I'm going to add to this flask 2 things. The first thing is the sodium acetate, which is 1.36 grams. So I'm going to add 1.36 grams of NaC2H3O2 trihydrate. And then I'm also going to add 7.34 milliliters of 1 molar HCl. And then add enough DI water to the mark. This is just a 100 milliliter volumetric flask. Okay. Now, when you make this, it's important because you're dissolving a solid, right? Add your sodium or whatever the solid is into the flask. Add the amount of strong acid or strong base. Add a little bit of water, okay? And then make sure that that solid completely dissolves. And then add all the way to the mark. Because if you add your solid and then you add water to the mark, you're going to see that eventually that line, the bottom of the meniscus at the mark, is actually going to decrease because there's a volume decrease as the solid becomes hydrated. So just make sure that it's completely dissolved before you add water so you don't have to worry about that. Otherwise, it will adjust your pH. If you do this correctly, theoretically, the pH of this solution should be 4.30. And we're going to test the pH using an electrode. If you look at the manual, it says that you are not allowed to pick up a hydrogen electrode, just like we did last week, until you have completed these calculations, which is why you're supposed to have these done before you walk into lab. All right. So now we can actually fill out the table in the very last page here, right? This is table 2 as it's seen in your lab manual. So if I go to the manual here and go all the way to the bottom here, let's Let's see, did I go too far? Yes, I did. Right here, buffer preparation summary. This table has to be filled out before you walk into the lab. If it's not filled out, I will not let you start. You will get a 0 and I'll see you in class. So make sure that this is completely filled out. So I'm going to answer with my assigned pH, my version of the table. You see, it's a little bit different, but it's asking the same questions. The first couple of questions are really, really easy to answer. Okay. First question is, hey, what's the assigned buffer pH that you were given? Well, for this question, I was assigned 4.30. So that's what you write down. What is the concentration of the buffer to begin with? Well, the concentration of the buffer is going to be equal to 0.10. And I do believe that everybody's concentration of the buffer will be 0.100. Don't take my word for it. Double check the manual, but I'm pretty sure that's the case. The milliliters of the buffer, the volume of the buffer solution is going to be 100 milliliters for everybody. So that's going to be the same for absolutely everybody. 100.00 milliliters. The chemical formula of the weak acid, or the acid form of the buffer. In this case, because I chose acetic acid and acetate ion, the acid form is acetic acid. So I'm going to write HC2, H3, O2. The pKa of the weak acid, you have to determine on your own, which in this case, for me, was 4.74, because that's the pKa of acetic acid. Again, you want to choose a pKa that's really close to your assigned pH. The chemical formula of the conjugate base of this acid is just the acetate ion. So that's going to be C2, H3, O2 minus. The chemical formula for the solid of the acetate ion. Remember, I'm not weighing out acetate ion on the balance. I'm weighing out the salt. The salt is sodium acetate trihydrate. The amount of the solid required to make my buffer solution is 1.34 grams. And the amount of HCl or sodium hydroxide, you have to choose one. In your notebook, it's going to ask you to circle one of these. I'm going to add HCl, so I'm going to circle HCl, and the amount that I have to add is 7.34. This is all you need. Once this table is filled out, you are more than welcome to start the laboratory. But again, when we actually do the lab on Monday and Wednesday, I'm going to check that everybody has completed it. And if you have not completed it, then you get a 0, you go home. All right. That concludes it. It was a little bit longer than I expected it to be. I thought that this discussion was going to be like no more than 30 minutes, but I guess it was a little bit longer than I thought. Of course, if you would like me to check your responses, you could check with me. I'm going to create a really, really, really big Excel sheet. Not a big Excel sheet, but just a big enough Excel sheet to do the calculation for me so that I can check if your answers are correct. All right. So if you want to take the time to check your work with me, you are more than welcome to email me your responses, and I will tell you whether you are correct or incorrect. I'll tell you where in your calculation, like which of the values is right or which of the values is wrong. And that's that. All right. I hope this was informative. I hope this helps you in your calculation. And I know that we have like 4 days left of our spring break, Friday, Saturday, Sunday, and today. So have relaxing as much as you can for the remainder of the week. And I will see everybody either on Monday or I'm going to see everybody on Tuesday. So, and that's that. Later.